Okay, in this video we're going to look at a technique called locational cost volume profit analysis. And to be honest with you, I'm not sure why the profit is in there, because the way it's typically done, we just look at overall cost. So the scenario here is we have three different locational options, options of where we can put a facility to do production. And so we want to find out, we typically in these kinds of decisions, we're looking at different fixed costs and different variable costs depending on which location. So each of these production facilities would be different sizes, have different layouts, would be different from each other in a way that's going to impact the fixed cost of operating them, but they also will impact the variable cost per unit of output. This is a classic trade-off of fixed cost versus variable costs. In most cases, not all, but in most cases, generally when you pay a higher fixed cost up front, you can produce at a lower variable cost per unit in the long term. So here we have three locations. We'll call them A, B, and C. And each location has a different fixed cost of operation. So this would be your annual estimated fixed cost of operation for that particular location. And this is an estimated variable cost per unit of output. So what we want to do is we want to look at our range of possible volumes that we want to evaluate over, and we want to, in essence, use the equation that represents that location's total cost at each volume level. So your volume column is basically your X values. This is your independent variable. And your cost columns, one for each location, represents your Y variable, the total cost at that volume of output. So in each one, we've used the basic linear equation, Y equals mx plus b, and that linear equation represents the linear cost function for that particular location, where M is your variable cost per unit, B is your fixed cost, and Y is the total cost. So all we did here was multiply the variable cost per unit times the volume and added the fixed cost. That becomes our linear function for location A. And then we can just repeat that equation across the range of volumes. Now, an important point, you need to be careful when you're doing this that you cover the entire possible range of volumes that you want answers for. So in other words, if you want to know which would be a preferable location at 3,000 units per year, then you need to make sure that your volume goes at least to, and preferably a little bit lower than, 3,000 units per year. Here we've evaluated from 4,000 units of annual output up to 13,000 units of annual output. So again, this is our equation for the A location. This is our location, or our equation for the B location. So you can see it's pointing to the fixed and variable cost for location B. Now, one important point, you don't want these two cells' values to change. So if you're not already familiar with this, what you want to do is when you type it in, or when you click on the cell, it'll go in as O3. But you don't want O3 to change. You want it to stay fixed. That's called an absolute reference in Excel if you're not familiar with that. There's a little simple Excel trick. If you hit the F4 key, it toggles through absolute and relative references. So if I hit it once, it becomes absolute column reference and absolute cell reference, or row reference. If I toggle again, you'll see it changes to the column reference is relative and the row reference is absolute. If I hit F4 again, it'll toggle again and make the column reference absolute but the cell reference relative. hit F4 again, it becomes all relative, and then one more time, and it goes back to an absolute, or an absolute to both column and row. And again, put the formula in once, use the drag handles to click and drag and repeat the formula, and as long as these two cell references are absolute, you'll be fine. So now what we've got is we've got three, in essence, lines, three linear functions extended through these values for x. And what we want to do next is we want to put these into a chart so we can actually see a visual representation of each one of these locations and its total cost across these range of volumes. So in Excel, we're going to go to the Insert tab. We're going to insert a line graph. Don't need anything fancy here. We don't particularly need to see data points, and I'll get to that in just a moment. So we're just going to do a plain old line graph. Now right now Excel doesn't know what data we want in the line graph, so it created a blank one for us. Sometimes Excel will guess, and it may guess correctly. In fact, in a lot of cases it will. It may not guess correctly. But what we want to do here is right click in the chart area. So right click, and we want to choose Select Data. This is where we're going to choose the data that's displayed in the line graph. So we select Data, and what we want is a data series. We're going to end up with a data series for each one of these locations, A, B, and C. So I'm going to add a data series. Let's make it a nice, intuitive name. Let's call it Location A. Now Excel will always pre-fill this equals 1 in braces. I don't know why, I don't know what that represents, but we'll just delete it, and then we'll click on the button to input the cell range to Excel. We'll click here, and then all we're going to do is click and drag top down on Location A, and that will give us the Location A series. Hit Enter, hit OK, and we've got our Location A line. Now we're going to add another one for Location B. Again, delete the values, and then click and drag top down for the B values. Click OK, and then one more data series for Location C. I clicked Edit. We want to add. Same process. Now, it's important to use the same direction. When you click and drag to select cells in Excel, it's important to use the same direction. And I'll get to what will happen if you don't, or what can happen if you don't in a second. Click on OK. Now, we've got our values. Remember that these are our total annual cost. That's what these represent. It may be helpful to format these in a minute to show them with a dollar sign in front of them. But this is the y-axis, gives us our total annual cost for each location at each volume. Let's do one more thing and go over and edit the x-axis labels. We'll click and edit them. And what we want to do here is put in the x values so they display at the bottom of the chart. Click OK. Click OK, and we have our chart. Now this chart's small. If you want to move it into its own data sheet, which I recommend, so you can see a little more detail on it, not in the data area, but in the main area of the chart, you can right click, you can choose Move Chart, and then just move it into its own data sheet. And there you have your chart. Now I'm going to go to one that I put axis labels on. So again, here we see the cost in dollars on the y-axis. Here we see the volume on the x-axis. We can zoom into this. What we're looking for is we're looking for the range of volumes at which each location is lowest. So we see at low volumes, and by the way, you can tell from the line that from 0 to whatever this point is, location A will be the cheapest in terms of total annual cost. Now, if you look at this, we can estimate it looks like it's about 6,500. We can get the precise number in just a couple minutes. From whatever that number is, from 0 to whatever that number is, A is the cheapest, lowest cost alternative. At this point, location B becomes less expensive, and from this volume to this volume, which looks like maybe around 10,000 units per year, the red line is lowest, which means that location B has the lowest cost. At volumes above that point, again it looks like around 10,000, through infinity, location C will be the lowest total annual cost. So how do we find out where these lines exactly cross? Well, it's pretty straightforward. We're going to go back to our equations here, and we want to find out where the AB line cross occurs. So what we're going to do, let me make a little bit of room here. What we're going to do is we're going to set the A equation equal to the B equation. So this would be the point. Let me just put a little apostrophe here so Excel doesn't think we're trying to put in a formula. This is the point at which the A equation equals the B equation. So this is the point at which 120x plus 120,000 equals 100x plus 250,000. This is the A-B point where they cross. We're going to do the same thing with the BC, except for the BC, it's going to be the point at which the C equation is equal. So that's the point at which 80x plus 450,000 equals the B equation value, 100x plus 250,000. And I believe, I'm not going to fuss with solving these right now, but I believe that they are actually 6,500 and 10,000. That's not always going to be the case. So the end result here is from 0 to 6,500, I believe it is, A is cheapest. From 6,500 to 10,000, B is cheapest. And from 10,000 up, C is cheapest. So now that we have that information, we'll use it to make a location decision based on our current and projected future volumes. So if our current volume, let's say, is 5,000 units of output per year, and we're looking at projected or forecast sales increase over the next 10 years up to 9,000 units per year, then we know that for the first part of that, location A will be the cheapest, and they're actually equal at this point. So in this range, from right now going out to this point, location A is preferable. From here to here, location B is preferable. So now we have a little bit more data in which to drive our decision. It's going to be more expensive up front, but how much time are we going to spend in each one of these volume ranges? And in that case, location B would probably be our selection, for the simple reason that in the long term, it's going to cost us less money over the next however many years we're evaluating. Straight up locational cost volume profit analysis.